next up we have Emily Law. She's going to tell us about visualization and analytics using NASA's Moontrek. Emily is a Deputy Program Manager and Development Manager in 2 directorates covering data systems and solar system research and Earth science.
Okay, great. Thank you, Ben, for the introduction. Hi, everybody. Good morning. It's an honor to be invited to speak at this virtual meetings. I would like to thank Ben for the invitation and also thank you all for your participation. As Ben mentioned, for over 20 years, I've been working for NASA Jet Propulsion Laboratory, where I wear multiple hats, including program and project management for the Earth, Lunar, and Planetary Science Data System. My passions lies in making NASA and JPL's data easy to be found, accessed, to be visualized, and used for science, for exploration, and for decision making. So today, I'm taking this wonderful opportunity to introduce NASA's Solar System Tracks, a project that I manage, and to share with you the Moontrek portal, which is a component of the project. Moontrek is an interactive web portal in support of planning and execution of lunar missions, not only for NASA, but also for its international and commercial partners. I do hope to convince you that Moontrek is a valuable tool for you to find, visualize, and analyze the wealth of data returned by past and current lunar missions. All right, Solar System Track projects provide a powerful planetary GIS platform. The project offers a suite of web-based GIS portals that provide visualization and analysis capability for mission planners, scientific researchers, as well as the general public around the world to easily access and view large amounts of data in 2D and in 3D, as well as to perform analytics of the data from various missions for a growing number of planetary bodies. When go to track.nasa.gov on a web browser, you will find 8 track portals that you can use to explore 8 different distant worlds at your fingertips. In addition to the interactive portals, we also provide data access and service APIs and standardized protocol for external users and platforms to interact with our data and tools via programmable interface. I would say that Moontrek is the poster child of the project. It is most sophisticated and well-developed, the first among the 8 available track portals. I believe it is useful for this community and audience because Moontreks offer loads of remote sensing data products and has the longest list of advanced capability, which I will touch on a bit later. Next, I'll use a movie to demonstrate what you can do with the track portals, but using Moontreks as the primary example. Just keep in mind that everything that you see is something you can do on your own. And please use the URL track.nasa.gov to visit Solar System Track's home site. It has a collection of supporting materials, including Feature of the Month, where a new article highlighting an interesting location is posted each month. The Did You Know section provides narrated movies created by using the track portals, and they are excellent example of science storytelling. The virtual reality library has a set of pre-made VR trips designed for use with smartphones and cardboard-compatible VR goggles. Here you can choose VR flyovers of some interesting lunar locations. On the home site, Explore Tracks give you the list of portals you can access. I'd just like to point out, in addition to Mars, there is an enhanced version that we welcome you to beta test. And note that we just earlier this month, a brand new portal for the asteroid Ryugu was added. Let's explore the moon using the Moontrek. The portal starts by giving you this option to take a short tutorial, which I would recommend for the first time use. There is this publicly available list of tools that can be found on the tool menu. However, if you have an account and login, the menu will expand to include additional analysis tools that are limited for advanced users, and I'll go into more detail about this later. What's shown here on the map is Moontrack's global base map taken by the Lunar Reconnaissance Orbiter's wide-angle camera. Like other lunar GIS platforms, it is easy to pan and zoom across the surface of the moon. Here we'll zoom to my favorite crater on the moon, Tycho. For questions such as how wide is this crater, you can use the distance tool to measure its diameter, just simple as drawing a line. If you want to know how deep is the Tycho crater, just as easily you can generate an elevation profile across the crater. Again, just draw a line. And the values from available DEMs on the Moontrack that intersect the path are shown on this plot. The graph shows the measurements, the height of the mountain and depth of the valley. Moontrack also makes it easy for you to save the numeric result of such a plot to a spreadsheet for your later analysis. Using the Generate 3D Print File tool, you can draw a rectangle around anywhere in any area of terrain that you want to create an STL or OBJ output file that can then be sent to a 3D printer in order to make a physical model. Here, it shows an example of the Tycho crater model from a 3D printer. In addition to the pre-made VR library available on the Solar System Track home site, Experience Track VR 2 allows you to draw any path you want anywhere across the surface. And when the path is done, a QR code associated with your path will pop up for scanning using your Android phone or just pointing at it with your iPhone camera. A link will then be provided to you for you to download the data onto your phone. And after that, just slip the phone into a pair of inexpensive cardboard compatible goggles, and you'll be able to fly across the path in VR. We have given VR demos at various public venues, such as this one, a Little League baseball game, and kids just love it and line up to try it out. Now, Moontrack hosts many lunar data products from a variety of instruments on board of past lunar missions such as Apollo, Clementine, Lunar Orbiter, etc., as well as the current mission like the Lunar Reconnaissance Orbiter, LRO. Now, Moontrack facilitates data discovery through a number of search options, including text, mission, instrument, product type, and spatial search. Here is a demo of finding data by using a search box. A polygon is drawn around the Tycho crater here, and the result data products available in the polygons are shown on the list. By moving the mouse down the list, their footprints will be revealed on the map. And when a data product is selected, you can add it to be displayed on the map, download the data, and even view or download its metadata as well. Now, track portals provide you also the ability to visually integrate data sets from different instruments simply by stacking and blending them together to create a customized views, which can then be easily shared with others. To demonstrate, we'll head to the Marius Hill using the Fly to feature. This area is known to have the most spectacular concentration of volcanoes on the moon, but you cannot tell by just looking at it with just the base map. However, what you can do is to view the area with other data sets. In this example, text search is used to find the DEM that combines the data from LRO's laser altimetry instruments and Kaguya's terrain stereo camera. And then it is added to the base map. Now you can see that the volcanic cones really pop out. Next, we'll add another layer called the Kaguya colorized gravity map on top of the same area to get a completely different view of Marius Hill. This data product is quite popular and often used as a model for lunar gravity field simulation and inversion studies. Then you can use the layer menu to control and change the opacity by using the transparency bar. And with that, Now you can clearly visualize the surface topology of the volcanic field as well as the now solidified, unerupted magma chamber beneath the complex here. When you're done adding all the data sets you like and creating a view that you would like to keep or share with the others, you can easily create an iframe to be embedded in your own website or send the URLs to others. And when the recipient invokes the URL, Moontrack will show the same view and know the same data sets of data products that selected previous by you. Now, Moontracks allow you to view data on Moontrack in other projections as well, such as polar projection for the South Pole and the North Pole of the Moon. But when in the 3D globe projection, you have the ability to use the game control keys on your computer's keyboard or a joystick device, or even a 3D mouse to maneuver, fly over across the surface. Just like this as an example, here we're flying down to the Tycho crater floor towards its central peak. These features really allow you to go flying through realistic and spectacular view of the lunar terrain. So to quickly reiterate, Moontrack offers a basic toolkit. In this tools menu that is publicly available, you can find the common tools that's readily available for use without having to log in. However, more complex and the type of analysis that you would like to do, particularly that are uniquely designed and targeted for exploration and science, are available for registered users only. Why, you may ask? Not only that they are not appropriate for the public use, but more significantly, they require enormous amount of CPU power, memory, and data storage to process the large volumes of data. When the system is built on a scalable backend infrastructure that leverages a hybrid computing platform, including Amazon cloud services and storage, it could really impose substantial cost and resources for the project to support the use of this type of tools. But no worries, if you don't have an account and have legitimate research needs, you are welcome to register. I only ask that you share with us your use cases and why you might want to use those advanced tools. I'll just take a sip of water before I continue. Hold on. So I'll give an introduction of each of the analytic tools in the following slides. Okay, many of the data products available on Moontrack are huge in size. For instance, the size of Kugoyer ortho mosaic is about 500 gigabytes. You would probably only want to create subsets of such large data sets for your research activity. In such case, this subsetting tool comes quite handy when you want to just select targeted area of interest that is smaller, representative, or a focused region you need to work with in order to make it much more manageable for your own processing and computations and manipulations. The result would be download and open for viewing automatically. The rendering speed obviously will vary and highly dependent on the size of the area you are choosing, the available bandwidth, and also the model of your machine. Now, Moontrack's crater detection tools support crater counting and investigation of craters. It is an image-based tool that finds crater on LRO narrow-angle camera NAC images. It uses edge and lighting condition detection techniques and also a recognition algorithm via a machine learning convolutional neural network to find all the crater candidates. You select an area by basically drawing a bounding box and then pick any of the available net images in that area as the input. And the output of this tool would include a heat map based on crater density, an image with craters that's labeled by bounding boxes over detected craters, and also a text file that lists the latitude, longitude, location, the estimated diameter and depth, and also associated confidence value for each of the craters found. Moontrack's rock detection tools support hazard analysis. It is also an image-based advanced tool. It uses classic computer vision techniques to identify rocks on LRO net images. The tool was built on techniques including gradient computation, image sharpening and contrasting, as well as threshold application and analysis to find as many rock candidates as possible. You select the area of your need and then pick any of the available net images in that area as the input. And the outputs of the analysis of this image would include an abundance chart based on the rock density found, an image with rocks labeled by bounding boxes, and also a text file showing the rock coordinates in basically image pixel space. Slope analysis is not an image-based, but instead is centered on elevation data. It estimates gradients and slope data on a given digital elevation map. It uses different convolutional filters and algorithms to compute gradient estimate of each point in the digital elevations terrain model by sampling the neighboring points around it. And once again, you limit an area using such as bounding box, and then an available DEM in that area as the input, and the output of the slope analysis would include a topographic map showing contour lines and also a file that contains the gradient values in GeoTIFF format. Now, Moontrack's surface lighting analysis tools, it models the direct and reflected scatter light and estimate the amount of light across the surface available as a function of time. It uses a ray tracing technique and takes into consideration of orientations of the sun, the moon, and Earth, and also the effective albedo of the Earth, as well as the lunar topography. You specify a start time and an end time, along with the time intervals for the modeling of a region. And for each time increment, the tool would output an irradiance plot of watts per square meter, a text file that lists the lat long and associated irradiance value, also a simulate GeoTIFF image files. Combining all the GeoTIFFs for all the time interval would then yield an animated simulation like the one that's shown here on the slide. Lighting modeling and analysis are really helpful for mission planning. For example, just to find how much sunlight would be available, I think it's really important when you are tasked to design a rover and its true path that depend on, say, a solar panel. Surface electrostatic potential tool calculates ionization potential due to solar wind striking the lunar surface over time. It uses a surface plasma modeled algorithm developed by Dr. Bill Farrell, who is a well-known plasma physicist at NASA's Goddard Space Flight Center. The algorithms include comparison of the surface ion flux and the solar wind ion flux. So all you need is just to select the area of interest. And outputs of the analysis would include a distribution map, a plot of electrostatic potential values relative to the solar wind, And also a plot shows the ratio of the surface ion flux to the solar wind ion flux. Now, in addition to the analytic tools that I talk about, and specifically in support of lunar exploration and science, we have developed a data pipeline that provides a turnkey and automated workflow that can create high resolution stereo elevation and orthomosaics from orbital imageries. This pipeline automates stereo pairing selection based on overlap regions, sun angle, spacecraft geometry for user-specified region. The workflow includes stereo reconstruction, excuse me, alignment, and also it excludes outlier points and remove the distortion of the mosaic for the output. For ease of use, in conjunction with the DEM mosaic, the pipeline also produced an associated ortho mosaic that is color balanced. A few examples of the output there, you can see it on the slide. There are other tools being developed for science and exploration applications. They include a calculator that determines the line of sight between two objects, a feature detector that classifies and detects a given type of features such as lunar rail, lunar pits, etc., in addition to lunar craters and rocks. A path tool that finds the optimal route between 2 points on the surface of the moon based on the slope analysis. We are also actively working with a number of international partners. For example, our current collaboration with Italy's Frascati National Laboratories produced a beta version of the lunar laser retroreflector tool. And our work with Germany's Max Planck Institute leads to a rockfall detector that finds rockfalls in LRO images. Just a little bit more about our work in progress. The purpose of the line of sight calculator is to identify visibility and also communication feasibilities between two objects as a function of time. The calculation is done using planetary geometries and also elevation data. For example, you can get the line of sight between a rover on the surface of the moon and LRO, or between a point on Earth and LRO, or between points on the moon and the Earth, or also 2 points on the moon, taking into consideration of its topography between them. Currently, we have a prototype that is accessible only through API. Work is still in progress, and we plan to make the tool available on Moontrack by hopefully the end of this year. The Lunar Laser Reflector tool is intended to support planning for future lunar reflector and ranging deployment. It also supports current and future reflector research on lunar interior and precision tests of general relativity. It is being used to predict relative geometries between Earth laser stations, the reflectors on the surface of the moon, or the reflectors on a rover, and also the lunar orbiters. And also to find images taken by the LRO showing reflections of the sun or lasers of the reflectors. The output of the tool include time intervals for viewing a solar gleam from the reflector, as seen from the LRO using a map view that displaying the positions. Other inputs include LRO net images that are available in the planetary data system that have reflectors in their view, and images available in planetary data system that have the solar gleam of the reflectors. As I mentioned, the beta version of this tool is already available on Moontrack. This rockfall tool is developed by Valentin Pico at the Max Planck Institute. It uses machine learning convolutional neural network to define rockfalls in net images. And finding where the rockfalls are on the moon is useful to study the seismic activities and also erosional state of the lunar surface. Recently, a global rockfall map was actually created using this particular tool. And currently, we are integrating this onto Moontrack. And when it's available in the fall this year, you will be able to select an area as input, and then the tool will return to you a rockfall heat map showing the distribution and density of rockfalls, a text file describing the map, the latitude and longitude, and also estimated size of each rockfall. So in summary, Moontrack is being used by NASA, other space agencies, industry, missions, scientists, and also the public to explore and study the moon. Our goal is to make it easy for lunar mission planners, scientists to find, visualize, and analyze the large amount of data returned from a variety of lunar missions, and also to facilitate sharing those data with the public and inspire our next generation. NASA is committed to continue enhancing and improving solar system tracks and its toolkits. And I would love to get your feedback to help us make Moontrack more effective and useful for you, and certainly for the lunar community at large. In addition, welcome any collaboration opportunities, whether it is a opportunity to create new innovative tools, or just to host any new data sets and analysis tool that you might want to share with others. All you need to do is just shoot me an email and I'll be more than happy to discuss those opportunities. I look forward to hearing from you. So in closing, I'd like to thank you all again for your time and attention, and also thank all of our sponsors and partners for their continuous support. With that, I'm going to stop, have a sip of water, and then I will be ready to take any questions you might have. Thank you very much.
Well, thank you, Emily. That is an amazing tool. I'm sure there's going to be lots of questions about it.
Thank you. I appreciate that. You're very kind.
Oh, no, it's incredible. I can't wait to get on it and start playing with it.
Cool. And just want to remind you that there are other portals, not just the moon. There's the Mars that, you know, Robert talked about quite a bit, and some asteroids, and also icy moons, and for example, Titan. So yeah, go play with it. Yeah, and if you have any questions, just let us know.
Definitely. Jessica has a question. He says, hi, Emily. When considering the solar radiation flux at the lunar surface, is it possible to use that data for an estimate of the dose depth curves needed to develop radiation shielding for human habitation and robotic scientific instruments?
I believe that is, the answer would be yes, although I am not a plasma physicist, and I would think that Dr. Bill Farrell would be really the right person to answer it. But as far as my understanding, I would say yes.
Great. Sham Mohan asks, is there any plan to develop tools which can be used to simulate lunar landing?
Oh, that is a really good question. We would love to do that. And we have a long list of ideas we have to enhance the tools already to support lunar development. However, we don't have that on the list, but we can certainly add that onto the list. But I would like to let you know that what we are going to do is really based on our sponsor's priority, which is NASA Science Directorate as well as the Human Operations Directorate. So potentially, if they think that that is something that we ought to do soon, and we will do that.
Great. Rosalie Dietman asks, what coordinate system does Trek use?
We have different coordinates, I think. So we have different projections. They use different coordinates. I will have to go back and look at particularly which projection you're asking for to give you the answer.
All right, no problem.
Okay.
Joseph Cunningham had a question. Does Moontrek have a composition analysis tool?
Composition analysis tool. I would like to ask, what does it mean by compositions? Does it mean that allowing you to upload your own data sets, compose your own view? What does that mean? I mean, is it annotation for you to be able to go and annotate what the maps that we already have?
I would imagine he's just asking if there's a way to just find out what like the remote sensing data is showing that particular region is composed of, maybe.
Okay, so in order to find out that information, each product has a very detailed metadata. So what you can do is pick the data product that you would like, just find it, and then you can view the detailed metadata, and that would give you the provenance and how it was being constructed.
Okay. Sanket Korgankar asks, is there an online tutorial for the crater detection tool on Moontrek?
Unfortunately, we don't have an online tutorial. That is another task on the long to-do list that we have to create tutorial for each of the tool. But I do have documentations, and I would be happy to go over that as well as discuss and go into detail about each of the tools. If you're interested, just go ahead and send me an email.
Okay. Calvin Gluck asks, you mentioned an API. Where can we find documentation for using the API?
Okay, there's a set of API. On the home site, if you go to track.nasa.gov, there is a tab that you can get to detail of our features. And one of the features is to talk about our basically WMTS, which is the Web Tiles APIs that you can use to access our data. In addition to that, we do have documentation which is not available on the portal. It's for APIs that support search, support analytic tools. So if you're interested in those, again, send me an email. I'll be happy to share those with you.
And there's another question about the API. Could it be used by software application to make data calls?
Yes, that's why we have the data access APIs. So you can just use those for your program. Either you want to just get the data for your analysis, or you want to build another user interface to access the data, you are welcome to.
David Chernovfront asks, can mineral and water data currently be shown as an overlay on visual images?
Yes, if they are turned into a mosaic, a map, a visualized, the map, then yes, they can do that. So we do have mineralogy data products that you can overlay on top of the base map. We even have a temperature map from Diviner instruments on board of the LRO, and that we were able to give like a time series of the data.
Great. Connections Live is asking, Can you think of a way to connect with space advocates who will become proficient in using this tool?
Very good questions. We are available to give webinars, give tutorial, share, meet with whoever who's interested in these tools, and we'll be able to give them demos and I'll walk them through all the capability. Yes. Again, email me or go to the track portals, and then each one of them would actually have a link for feedback, so you can reach me through that as well.
Excellent. Joseph Cunningham asked, it's not really a question. So he said, finding the mineral composition of various parts of the lunar surface and subsurface from available data. I guess we'll just move on from that.
Okay.
Is there any data set that can overlay rover routes on top of the lunar map?
Overlay the rover route.
I think like if maybe you were planning some kind of expedition or something, if you could overlay that on top of the maps and maybe see where there might be obstacles.
I did talk about the path tool that potentially would allow you to basically determine the start point and the end point, and we'll find the optimal path. So one thing that we are working on is actually annotation, which is actually allow you to draw your own path. So in that sense, that is an overlay on the map.
Very cool. Are there any more questions for Emily? All right, it looks like nobody else has any questions. So thanks again, Emily. That was a fantastic presentation and an amazing tool.
Oh, thank you so much. I really appreciate this opportunity, and thank you all for your time, and again for the invitations. Again, I'm available. Just if you have further questions, just feel free to reach out to me. I love to talk about the tools. Okay, and have a nice conference, everybody.